Welcome. In this video, we're going to take a look at exponential and growth and decay. So we've already done some work with some exponential graphs and some exponential functions, but today we're going to start looking at writing some of our own equations from some scenarios. So when we have our exponential growth or decay, we're going to be looking at this function here. This is particularly for growth. And the biggest reason why it's particularly for growth is that we're getting bigger, we're adding something on. But we're going to start off with our A value here. So this A here is always going to be our starting amount. And this R here is our rate. Let's give that its own little color here. And then this X here is whatever we're going to plug in. Usually that's a time amount or something to that effect. So let's take a look at some examples here. After we look at what is exponential growth, it's when your original amount is repeatedly multiplied. And that repeated multiplication is what makes it exponential by a positive number called the growth factor. So in this case, the 1 plus R is going to be that growth factor. Okay, so let's look at some examples here. Our first one here, we have 30 deer. Let's keep that so we can start that. So we're starting off with 30 deer. That's our A value. Are relocated to a deer preserve. Their population increases. So that increases tells us that we are dealing with growth here. It's increasing by 50%. So that is our rate. And anytime we have a percent here, we want to think of that percent as a decimal. Write an equation to model this situation. So our beginning amount here is we have 30 deer to start. Our growth factor is that 1 plus R, so 1 plus 50%, but 50% is a decimal. So our equation then is going to be y equals 30 times 1.5 to the x. And x here then is number of years because that's when it is changing each year. So we're just taking those pieces and putting them together to make ourselves an equation. Let's take a look at another example. 8 penguins. Oh, we already know our beginning amount. We have 8 penguins are introduced to the San Diego Aquarium. If their population doubles each year, write an equation to model this situation. Oh, sorry, I used the wrong color there. It should be doubles. Okay, so this one we have to think about a little bit. We still want to do that 1 plus the growth, but think back to our starfish example. Right? If we're doubling, that means we're keeping our 100% and adding another 100%. So your growth factor is still 1 plus your growth. It's 1 plus 1, which ends up being 2. Beginning amount, we have those 8 penguins. So our equation here is y equals our beginning amount times our growth factor to the x, and x again here is each year. Hey, picking apart our pieces here. This would be a great place if you're feeling pretty confident. Pause and see if you do it on your own. Okay, Melanie received $350 for Christmas. We're starting off with $350. She put the money in a bank account, which grows at a rate of 4%. So we found two things there. It's growing, so we know we're exponential growth. And we have a rate of 4% each year. So we're in 4%. We also found out that it's each year, so our x values are years. Write an equation to model this situation. So we're starting with 350. For growth factor, we get to keep all of that 350 plus an additional 4%. Careful changing your percents to decimals. 4% is 0.4. So our equation here is that 350, so y equals 350 times 1.04 to the x. Okay. Given this equation, let's work our way backwards. By what percentage did this grow? So we're going to look at our growth factor here and think this is 1 plus R. So if I want to find out what R is, I need to figure out what did we add to 1. So R is just that 1/5. And what percentage? So 0.15 would be 15%. What was the beginning value? So that's still our starting value, our A value right here. We started with 2,500. Hey, next example, 24 rabbits. Oh, starting amount. Are introduced to Australia. Assume the rabbit population doubles every year. So again, we got to keep all of the rabbits we started with and we get 100% more. Our growth factor is 2. How many rabbits will be there in 28 years? This one's a little bit different. It told us it's 28 time periods later. Make sure that these years here match up with our years there. So our equation is y equals our starting amount times our growth factor to the x. But we know x, so we can put in place of this x 28. Right? So we are going to take 24 times 2 to the 28th. This is going to be a big number. 2 to the 28th grows really quickly. So let's see what it is. 24 times 2 to the 28th. We get that giant number. There are, let me write it down and then we'll make sense of it. Okay, so we have 1,000, million, trillion, 6,442,450,944 what? Rabbits. Okay, hopefully those are getting a little more comfortable. Let's just look at a few more examples of growth and then we'll move on to some decay. So this one, we have a bank account, grows at a rate of 6% a year. So we have 6%. We know our time periods are each year. If you open an account with $550, that's how much we're starting with. How much money will you have in 7 years? Okay, so our beginning amount, $550. We keep all of that 550 plus an additional 6%. And we're checking where is it after 7 years. So y equals our starting amount, growth factor, to the 7 years. Once we have it there, we can use our calculator to calculate what is that. 550 times 1.06 to the 7th. And so now our money is worth about, it's money, so let's make sure we round appropriately. $826, $827 after just saying we should round appropriately. Okay, last growth example, and then we'll move on to some decay. A certain bacteria doubles in population. Growth factor 2 every 6 hours. Ooh, careful here. That is our time period is 6 hours, each 6 hours. Given there were 100 bacteria to start with, how many bacteria will there be in 2 days? Those do not match. So I need to figure out how many 6-hour time periods are there in 2 days. So 2 days, 24 hours each day is 48 hours. How many 6-hour time periods in that 48? So if we divide 48 by 6, we should get 8. So 8 time periods is going to be our answer there. So because these don't match, I have to figure out how many groups of 6-hour time periods are within 2 days. So 2 days is 48 hours. Those 48 hours, if we split them up into 6-hour time periods, there are 8 of them within those 2 days. So then our equation here is 100 times our growth factor to our number of time periods. So 100 times our growth factor to our time periods is 25,600. 25,600 what? They are bacteria. Okay, moving on, we're going to do some decay, which really we're doing the exact same thing, except for if it's decay, instead of adding, we're subtracting. So we're getting rid of some of our We start out with all of it, and we're decreasing by some percentage. So for exponential decay, the growth factor is between 0 and 1. So it's going to be less than 1. Still be greater than 0. It has to be positive to be exponential. So first example here, we have in the early 1800s, there were estimated to be 50,000 grizzly bears in the United States. If the population declined by 20% each year, write an equation to model this situation. So beginning amount, so we're still looking for these same things. So our beginning amount, we had 50,000 grizzly bears. It's going down by 20% each year. So this is where a little different. We're 1 minus 20%. Okay, so 1 minus 20%, that means we have 80% of the grizzlies left. That's really what we want. So our equation here is y equals 50,000 times 0.8 to the x, where x is the number of years. Okay. Ryan's dad bought him a car for $15,000. That car depreciates 12% each year. Write the equation to model this situation. So beginning amount, 15,000. Okay, it depreciates. That might be a new word for you. That means that it loses value. So it depreciates in value by 12% each year. So our decay factor is 1 minus 12%. And so that 1 minus 12%, that's 88%. That's what we have left there. So we have f of x equals 15,000 times 0.88 to the x, where x is, again, the number of years, because that's our time period. Okay, so we have our equation here. By what percent is this decaying? So we're thinking 1 minus something, our rate is equal to 0.78. Okay, so if we subtract 1 from both sides, I get that my negative rate is, what, 22.22? Negative 0.22. So that means our rate is 22% that it's decreasing by. We're left with 78%. That means we've lost 22%. And what was the beginning value? Beginning values is this guy right here. So that's 18,000. Oh, that's wrong. 1,800. Added an extra 0 there for kicks, apparently. Okay, a couple more examples, and we'll wrap it up for this lesson. Sterling has a headache. It takes 400 milligrams of ibuprofen. The concentration of medicine decreases by 15% each hour. How much ibuprofen is in his bloodstream after 3 hours? So again, I'm going to check and see, do we have our hours, each hour after 3 hours? Those line up, so we don't have to worry about that. That's our time period. We started with 400 milligrams. It's decreasing, so we know we're using decay by 15% each hour. Okay, so let's see if we can put together an equation here. We have fx equals our starting amount, so 400 milligrams times 15% taken away from 100. It's decreasing by 15% to the x. So 1 minus 0.15 is 0.85. And then we want to know after 3 hours, so let's go ahead and plug that in. And we can figure out how much ibuprofen is left in his bloodstream. 0.85 to the 3. And we get 245.65 milligrams of that ibuprofen left in his bloodstream. Okay, a new car costs $25,000 and depreciates at a rate of 9% each year. What will the car's value be in 7 years? So again, check your years, match up with years, so your time periods match up. We don't have to do any work there. We started with a $25,000 car. It's depreciating, so again, that means it's losing value. So we're going to be using decay here by 9%. So our function here, f of x, is equal to our starting value, 1 minus 9%. Careful there, don't do 90%. the x. So we get 25,000 times 0.91. If we lose 9%, we have 91% remaining. I want to know the value after 7 years. So let's plug in 7 years for x. Okay, 25,000 times 0.91 to the 7th. And so your car's worth about, it's money, so let's label it and round appropriately to the nearest cent, since we're talking about money. So it's now worth about $12,919. Okay, very last one here, we're going to take a look at some caffeine. Caffeine is found in a wide variety of food products consumed by Americans. In fact, more than half of all adult Americans consume at least 300 milligrams of caffeine a day. Once in the body, it takes about 6 hours for half of the caffeine to be eliminated. So in science, we'll come across this a lot. We use it in dating and other things like that. This is called a half-life. So that means that you've lost half, but also you have half remaining. So anytime we're talking about this half-life, our decay factor is a half. You could still think of it as 1 minus a rate. It's 1 minus 1/2, which is also still 1/2. When an equation model the amount of caffeine in the bloodstream after 6-hour periods. So we started with 300 milligrams. We're losing half of it each 6 hours. So X here, this is important that your X, this guy, is this 6-hour periods. So if it was after 6 hours, X would be 1. After 12 hours, X would be 2 in each 6-hour period. So if no more caffeine is consumed, how much caffeine will be in the body 24 hours later? So we have to figure out how many 6-hour time periods is this. So just divide by 6, we get 4 time periods. Or 108 hours later, so let's divide that by 6. Don't know that one off the top of my head. We get 18 time periods there. So we're going to do 2 different calculations. First one, we're going to do how much is left after 4 of those 6-hour time periods. So 300 times 1/2 to the 4th is 18.75. Sure we label that, it's milligrams. And after 18 of those time periods, we're going to do the same thing, but we want to do after 18 time periods. And so after 18 time periods, there's about 0.0011 milligrams. So essentially it's mostly gone or essentially gone. So that's all I have for you today. Make sure that you take a look at, remember our growth decay rate here, that we're using the same type of thing. We're starting with 100% and we're adding or subtracting depending on if it's a growth or decay. All of these are exponential because we're multiplying by that rate over and over again. So thank you so much for watching. That's all I have for you.